Welcome to Section 6, which comprises the final 17 lectures of this course. And this is Lecture 44, in which we're going to be discussing what I call cracks in classical physics. This is going to be a different kind of lecture than the earlier ones. It's going to be rather historical. There's going to be no math. You will see two math symbols that I'll remind you of from earlier lectures, but no math development, no big screen monitor, no calculations, much more historical. And part of my goal at the beginning of this lecture is to put you in the philosophical mood of a physicist in the late 19th century, looking at physics as we understood it then. Because you have to get your mind into that mode of thinking in order to understand the dramatic effects of these cracks in classical physics, which I'll be introducing in this lecture. I'll introduce these cracks here, but I won't have a whole lot to say about their resolution. I'll leave them kind of dangling in your mind, and then in the next few lectures, we'll look at how each of these individual cracks gets resolved. So, beginning our sort of historical development here, let's go back and look at where we've been in this course already. We started out in Lecture 1, for example, looking at these realms of physics. And again, this was an arbitrary distinction of physics into 6 different realms. We could have divided it differently, but here's how we did it. We began with Newtonian mechanics, the theory of Isaac Newton and many others describing mechanical systems, how objects move. We moved on to oscillations, waves, and fluids, examples of more complicated kinds of motion. From there, we went to Section 3, thermodynamics and statistical mechanics, the physics associated with heat and other thermal phenomena. Then we spent a good long time in Section 4 on electromagnetism. Electricity first, magnetism later. They merged together to be, at the end, electromagnetism. We discovered, as a result of doing electromagnetism, that in fact we understood the nature of light. And so Section 5, although it was a separate section on optics, we came to understand as a branch of electromagnetism. Now we're ready for Section 6. And I've titled Section 6 Modern Physics, Relativity and Quantum Physics here in this Realms of Physics diagram. But I want to emphasize that the word modern physics is kind of a misnomer. Modern physics, used as a term in the history of physics and the descriptions of physics, refers to the physics since about the year 1900. So the turn between the 19th and the 20th century. That's hardly modern physics. If you want to talk about what you would think is modern physics, you're really talking about contemporary physics. So modern physics has been with us for well over a century. But that's what we're introducing here, the big ideas of modern physics, because they are still the underpinnings of the most up-to-date contemporary physics in the modern world, barring really brand new discoveries which shift physics into entirely new realms. So when I talk about modern physics, I'm talking about the physics that we have understood since about the year 1900, and what we're going to be focusing on in this lecture is that transition from the kinds of thinking physicists were doing in the late 1800s to the kind of thinking they had to do in the early 1900s and on up to the present. So let's have a little review of this classical physics, which was really the subject of the first 5 sections, although classical mechanics was really right at the beginning. We began with Newtonian mechanics. Newtonian mechanics made some very important philosophical steps in the nature of physics, the history of physics, the thinking about the physical world. And one of the most important one was this idea that the same laws apply to the terrestrial realm and the celestial realm. Before Newton's time, before Galileo's time, before the time of this great revolution in Galilean and Newtonian physics, there were the heavens, there were perfect motions up there, perfect circles. That was an entirely different realm, a different set of laws applied. Then there was the low base realm here of Earth where other laws applied. What Galileo and Newton and others succeeded in doing was for the first time linking the celestial and terrestrial realms and recognizing that the same laws govern both. So that was sort of the big philosophical breakthrough of Newtonian mechanics. Newtonian mechanics, from a more practical point of view for doing physics, is the recognition that what physics is about really, or what study of motion is about, is change in motion. Newton doesn't tell us why things move. He doesn't give laws about why you move at a constant velocity. He gives us laws about how motion changes. And that's a really big key concept, a key change from Aristotle, who felt that you need to push and pull, you need to exert forces to make things move. Nope, says Newton, you need to exert forces, pushes and pulls, and that causes change in motion. And as I indicated back in the Newtonian mechanics section, many of the common misconceptions about applying Newtonian ideas come from not recognizing that it's all about change in motion. Newtonian mechanics had another philosophically important point. Newtonian mechanics is deterministic. You give me all the forces acting on an object, and you give me the initial velocity and the initial position of that object, and how those forces may change with the object's position, and I can predict its entire future history, or its entire future behavior. You do the same for every particle that makes up the universe, and in principle, if you give me at any time the positions and velocities of every particle and the forces that act between those particles, then I can predict the entire future of the universe, and that future is therefore, at least in some philosophical sense, even though I might not be able to do all those calculations, that future is completely deterministic. Then we extended Newtonian mechanics. We extended it to oscillations and waves, oscillations being back and forth motions typically of single objects, sometimes composite objects, but mostly single objects, and then wave motion in which we have a medium like, say, air or water or a bunch of springs linked together, in which motion in one part of the medium gets transferred through mechanical forces that we understand with Newtonian mechanics to other parts of the medium, and that transfer of motion transfers energy, and that's what we mean by a wave, something that transfers energy but not matter. And I'm emphasizing these ideas here because they're going to come back to haunt us when we talk about this transition to the physics of the 20th century and beyond. We looked at fluid dynamics, another example of a complicated system with too many particles for us to count and keep track of, but the ideas of Newtonian physics still applied. We did the same thing to statistical mechanics as the basis of thermodynamics, the study of heat, and we did that mathematically for the case of the ideal gas, which was bouncing off its container walls. Momentum was conserved, energy was conserved, and we worked out an understanding, for example, of the nature of temperature, the meaning of temperature, based ultimately in Newtonian mechanics. Then we move to Section 4, Maxwellian electrodynamics, which seems to be an entirely separate realm of physics. We had electric charge, a basic property of matter. We had electric and magnetic fields to describe the interaction first of charges and later of the fields themselves, charge and field interactions. We ended up with 4 equations that described all of classical electromagnetism, the famous Maxwell equations. And when we looked at those equations carefully, as Maxwell did back in the 1860s, we discovered that they admit the possibility of a new kind of wave, waves that are waves basically of electric and magnetic fields continually self-regenerating each other by the processes of electromagnetic induction, and that carry energy through space at, we found out, speed c, the speed of light. So these waves follow from Maxwell's equations. They have this speed, the speed of light, and we recognized, or Maxwell recognized, that they include light. And that made optics a branch of electromagnetism. So Section 4, electromagnetism, got us an awful lot of new physics, including all of optics. Now, to put you again in this mindset of classical physicists in the 19th century, remember Maxwell is coming up with his theories in about the time of the Civil War in the United States, in the mid-1800s. The mechanical view of Newton had been so successful that physicists tended to think of electromagnetism in a mechanical way also. For example, Faraday, who introduced to us the idea of the law of electromagnetic induction, that changing magnetic fields make electricity in some sense. Faraday felt the lines of force, what I've called electric and magnetic field lines, he felt they were physically real things stretched out there in physical reality, and they could have stresses in them and pulls and pushes, and this is where electromagnetic forces and so on came from. So there's an attempt to reconcile electromagnetism with this mechanical view. Maxwell himself thought of electric and magnetic fields as mechanical phenomena in what he called the electromagnetic ether. And this ether idea is going to haunt us in the next few lectures. It's the idea that there is some substance that permeates the whole universe. And in particular, the electromagnetic ether is this substance in which electric and magnetic fields are ultimately mechanical stresses and strains. And again, this is the mindset of these physicists in the 19th century because the mechanical view had been so successful. So electromagnetic waves, which are disturbances of electric and magnetic fields, become disturbances of this ether in the same way that sound waves are disturbances of the air, or water waves are disturbances of the surface or bulk of liquid water. Here's the only math in this lecture. You'll remember the constant K that came into Coulomb's law that described the electric force between 2 point charges, or equivalently gave us the electric field of one charge. And then we had an equivalent magnetic constant mu naught, mu sub 0, as the corresponding magnetic constant. Those in this mechanical view become properties of the ether. They tell how the ether responds to electric and magnetic fields. And here is a clip from a paper that Maxwell published in 1861 called On Physical Lines of Force. So on the left you see the just heading of that paper. On the right you see a picture from in there, a figure that Maxwell drew, in which he pictured electromagnetic phenomena as involving sort of gears, invisible hidden gears and rotations in this electromechanical or electromagnetic ether. So classical physics at the end or middle to end of the 19th century is a physics in which there's mechanics, well understood, there's electromagnetism, also well understood, summarized by Maxwell's equations, and now attempted to be understood as a mechanical phenomenon. So there is this mechanical view. That's the view that basically has to go away. It has to be swept away in several big revolutions, two in particular, the relativity revolution and the quantum revolution of the early 20th century. So let's now turn to take a look at those so-called cracks in classical physics, and we'll see, by the way, that most of them involve electromagnetism, all but one. In fact, that one involves gravity. So let's take a look at what these cracks in classical physics, in fact, are. One crack I'm going to call ether quandaries. As I've hinted, this ether that Maxwell and others came up with, it was supposed to be this medium in which electric and magnetic fields were stresses and strains, and therefore in which electromagnetic waves were propagating disturbances. That's going to cause a lot of trouble. That is clearly based in electromagnetism because it involves this electromagnetic ether and electric and magnetic fields and waves. There are quandaries involving Mercury's orbit. By the way, some of these quandaries I'm mentioning here, some of these cracks are very dramatic. There are just extreme disconnects between what physics predicts, theoretical physics predicts, and what observation or experiment shows. Some of them, like this one involving Mercury's orbit, are very, very subtle effects. There's problems involving glowing objects, hot objects that glow hot enough to give off light. There are cracks involving the behavior of electrons and light, the interaction between electrons and light. And finally, there are cracks in classical physics that involve the very nature and, in fact, the very existence of atoms. So in the rest of this lecture, we're going to look at these 5 different cracks in classical physics. I'm not going to resolve them here, but I'm going to get you primed for trying to understand the resolution. And I want to remind you once again that of these 5 quandaries, all but the one involving Mercury's orbit, which is a kind of gravitational quandary, all the others have something to do with electromagnetism. So we had mechanics, we had electromagnetism, we had 19th century physicists trying to make electromagnetism work mechanically, and maybe that's where the problem is. So let's begin looking at some of these ether quandaries. The ether, first of all, is an improbable substance. It's got to permeate the entire universe. We know that because we know that electromagnetic waves permeate the entire universe. We can see light from distant stars. It's also got to be a very stiff substance because the waves propagate at that very high speed of light, about 186,000 miles a second, 300,000 kilometers a second. It takes a stiff spring, for example, to make a rapid propagating wave on a spring. It takes a stiff substance. The ether had to be stiff, and yet the planets and the stars had to be able to move through it essentially without resistance. So it's improbable. It's also improbable for a slightly more subtle reason, which you can understand having done Lecture 18 on waves. In Lecture 18, I introduced the idea that some waves were transverse waves, the disturbance, like more or less the surface of a surface wave on water. The disturbance is at right angles to the motion. A water wave is sort of a mix, but close enough. Other waves, like sound waves in air, are compressional waves, longitudinal waves. The wave disturbance is in the same direction the wave is propagating. We know that electromagnetic waves are transverse waves. The electric and magnetic fields are at right angles to the direction that wave is moving. And that means the ether couldn't be a gas like air. It couldn't be a liquid like water in which the waves were going in the bulk substance of the liquid, not at the surface, but in throughout the liquid, because those kind of materials don't support transverse waves. So it had to be kind of more like jello. So that made it even more improbable. So it's an improbable substance. Another thing about the ether is it's the place where Maxwell's equations are valid, because Maxwell's equations talk about electric and magnetic fields as disturbances of the ether. So they're valid in a reference frame that's fixed with respect to the ether. If you're moving with respect to the ether, don't expect Maxwell's equations to be quite right. And the faster you're moving, the more obviously incorrect they're going to be. So we ought to be able to detect deviations from Maxwell's equations if we're in reference frames that are moving with respect to this mysterious ether substance. And in particular, the speed of light ought to be different in different reference frames. Just like if there was a giant wind blowing past me, sound waves would have different speeds relative to me, depending on which way they were going relative to that wind. Because sound is a disturbance of the air, and the speed of sound is the speed with respect to the air, not necessarily with respect to me. And it should be the same with the ether. The speed of light should be the same in the ether frame, namely c, 186,000 miles a second, 3 times 10 to the 8 meters per second. But if somebody's moving relative to the ether, or the ether's moving relative to that somebody, that observer, then they should measure different speeds for light. And in fact, the speed of light should be different in different directions. Now you might say, well, how do we know if we're moving relative to the ether? Well, we don't. Although I'll give you some philosophical arguments in the next few lectures about why we think we must be moving relative to it. But here's what we do know. We do know that the Earth is moving around the sun. It's doing so at about 20 miles per second, at about 30 kilometers a second. That's pretty fast. It's not super fast compared to the speed of light, but it's fast enough that you ought to be able to detect motions. Furthermore, Earth is moving around the sun, so it's moving in different directions at different times of year. And so Earth's motion relative to this ether ought to be changing, and we ought to be able to detect that motion. And the quandary is that we can't. And we'll spend a good deal of time on the experiments that show us that we can't, because that's a really big, important crack in classical physics. So in particular, we're looking at Earth's orbital motion as providing different reference frames as Earth moves relative to the ether. So here's the ether as this sort of background substance permeating the whole universe. Here's the sun. Here's the Earth's orbit. And at one time of year, the Earth is moving to the right here in this picture in its orbit. 3 months later, it's moving vertically in this picture. 6 months after we started out, it's moving to the left. And here it is moving downward in the diagram. Its motion relative to the ether must be changing. We may not know exactly what that motion is in some absolute sense. Maybe the sun is at rest with respect to the ether, but maybe the whole galaxy is, or maybe something else is. But the Earth's motion relative to the ether has to be changing, and so we should be able to detect differences in the speed of light in different directions. So that takes care of the ether quandaries. We'll spend a few lectures resolving them and then looking at the implications of that. Here's the second of those cracks, Mercury's orbit. In classical physics, classical Newtonian gravitation, the prediction is that a planet ought to undergo an elliptical orbit. Remember, the planet's orbits are almost circular, but they're slightly elliptical. So on the left, I have a movie here of Mercury going around and around in its elliptical orbit. What we in fact observe is that Mercury's orbit does not close on itself, but the whole plane, the whole axis of the orbit moves slowly with time. That's called precession. Now, some of that we understand it's due to the presence of other planets and other effects that are explained by Newtonian physics. But when you take those all out, there's an unexplained precession of 43 seconds of angle. What's a second? Well, you know what a degree is. A minute is a 60th of a degree, and a second is a 60th of a minute, a 3600th of a degree. And every century, every 100 years, Mercury undergoes a precession, very tiny, of 43 seconds. But nevertheless, it's there, and it's unexplained by classical physics. That's another crack. Let's move on to the remaining cracks. That crack, by the way, the Mercury's orbit crack, was the only crack that did not have to do, in a fundamental sense, with electromagnetism. It had to do with gravity. The rest of the other three now are different kinds of cracks. We're going to resolve them in different ways, but they're also cracks that ultimately involve electromagnetism. So let's take a look at something that we, in fact, worked on in earlier lectures. In lecture 22, for example, I did the demonstration I'm about to do here where I had a light bulb, and this is just an ordinary light bulb, different only in that it has no frosting on the inside to diffuse the light, so you can actually see the filament. And all I'm going to do is apply a variable electric current to that light bulb. And as I bring it up, you see it begin to glow. It's glowing. It's not very hot. It's not got a lot of electric current flowing through it. It's at a temperature that gives us a kind of dull red-orange glow. And by the way, what does this have to do with electromagnetism other than that it's an electric light bulb? That's not the relevant thing here. What's relevant here is the atoms in that light bulb in the filament of that light bulb are being jostled into more rapid thermal energy. Those atoms consist ultimately of electric charges, and we know that accelerated electric charge, we know this from lecture 40, accelerated electric charge is ultimately the source of those changing electric and magnetic fields that then go propagating off as an electromagnetic wave. So this is about electromagnetism. It's also about thermodynamics. And as I turn the current up, two things happen. And again, back in lecture 22, we talked quantitatively about one of those things, which was it got brighter. Because its temperature is higher, there's more current flowing through it. The temperature is higher. The atoms are jostling around more vigorously because, again, thermal motion is associated with temperature. Temperature is a measure of the average kinetic energy. That's going up. And so they're accelerating more, and they're giving off more light. And that was that T to the fourth in the Stefan-Boltzmann radiation law that I introduced back in lecture 22, and had to do with quite a few other aspects of the emission of light and electromagnetic radiation by hot objects. If I turn it up even higher, that T to the fourth brings the emission up more. But something else happens, and what else happens is that the color of the light changes. Now it's a kind of bright yellow-white. As I bring it down, it's a little more of an orangish color. As I bring it down, it gets to be a dull red, and finally fades into infrared, and I can't even see it. It's still on. There's still some current flowing, but it's in the infrared. Well, that is what, in fact, happens. What does classical physics predict for this? Well, classical physics, here's our next crack, the crack of glowing objects. Classical physics predicts that the energy from a glowing object should rise continuously with decreasing wavelength. Now, what you were just seeing with the light bulb was, as I made the light bulb hotter, the energy shifted towards shorter wavelengths from dull red to orange to a kind of yellow color, moving to shorter wavelengths. But what classical physics predicts is that the energy should rise continually with decreasing wavelengths, and because the shortest wavelengths known at that time were the wavelengths associated with ultraviolet radiation, we didn't know about X-rays or gamma rays, this was called the ultraviolet catastrophe. That is in complete contrast to the observation, which is that the energy peaks at a wavelength that depends on temperature. So here's a graph that describes this phenomenon. There's the actual observations. On the right are long wavelengths, on the left are short wavelengths, plotting on the vertical axis what I call radiance, the amount of energy emitted per unit of wavelength, and that is the classical prediction. That curve that rises toward infinity as we go to very short wavelengths, which again were thought to be, in those days, ultraviolet. Now we know even shorter wavelengths. The curve I've plotted, the actual observed curve, is for a 6,000 K object. That's about the temperature of the sun. A cooler object would have a curve that showed less energy being given off, and it would also be the curve associated with a lower temperature. So we have this very stark contrast between this classical picture that there should be infinite energy and the picture that there should be energy that peaks at some wavelength and then goes back down again. By the way, that infinite energy occurs because ultimately of something we talked about in the thermodynamics lectures just briefly, which is this partition of energy among different modes in an object that has thermal energy. And there are, in classical physics, infinitely many of those modes to partition energy, and that's ultimately where the ultraviolet catastrophe comes from. Okay, that's another crack in classical physics. Let's look at the last two. One involves behavior of electrons and light through a phenomenon called the photoelectric effect, which had been studied in, the 1880s and onward, when people were beginning to experiment with evacuated tubes, which were the precursors of the vacuum tubes, which powered electronics through the first half of the 20th century, a little beyond that, and then were replaced by transistors and solid-state electronics. So here's a typical experiment. We've got an evacuated tube, that rectangular thing. We've got a couple of metal electrodes in it. We're shining light on it, and the light energy is somehow able to release electrons from that metal, and we've got a battery and a meter hooked up, and we can measure how many electrons are flowing and whether electrons have been released, and we can put that battery in either orientation so it's positive on the left as it is now and attracting electrons, or we could make it negative and repelling electrons. So what happens? Well, first of all, electron ejection should take a while in this experiment. It should take a while because the energy is coming in the form of electromagnetic waves, and a given electron that's experiencing the electric force, particularly the electric force of one of these waves, is going to take a while to build up much energy. And it's going to take a significant amount of energy for that electron to be ejected from the metal it's living in. So it's going to take time. You turn on the light, you shouldn't get electrons immediately. Increasing the light intensity should shorten that time because the wave gets bigger. The electric fields get bigger. They impart more energy in a shorter time. And the electron energy shouldn't depend on the light's wavelength. Well, when you do the experiment, the electron ejection happens immediately. When you do the experiment, you find that increasing light intensity doesn't shorten the time. It happened immediately already. And you find that the electron energy actually does depend on wavelength. It increases with decreasing wavelength, shorter wavelength, higher frequency. And there's actually a cutoff wavelength that if you get longer than that cutoff wavelength, no electrons are rejected. Now, this is a fairly subtle experiment. It's not something obvious, but when you do this experiment, it does stand in stark contrast with the predictions of classical physics. And let me end with the last of the cracks in classical physics, the cracks that involve atoms. And here, there's a subtle and a stark issue. It was in about 1911, after a series of experiments, that Ernest Rutherford and several colleagues developed the idea of the nuclear atom. They discovered the atomic nucleus. They bombarded thin foils with high-energy particles coming off newly discovered radioactive elements. They found that rarely was there any interaction of these high-energy particles, but when there was, the particle bounced back vigorously. And that gave them the conclusion that there was in the center of the atom this very tiny but very massive thing called the nucleus. And out of that came this picture of the nuclear atom with the electron, in this case of hydrogen, going around the proton. Very simple. It's kind of like a miniature solar system. The orbiting electrons, though, are accelerated charges because they're going in circular motion. Remember, it's change that matters, and change in direction matters as much as change in speed. So that is accelerated motion. The orbiting electrons are accelerated. Accelerated charge is the source of electromagnetic waves. The accelerated charges ought to radiate electromagnetic waves. The electrons should lose their kinetic energy of their motion. They should spiral into the nucleus quickly, and my advanced electromagnetism students actually calculate the time. It's very short, and atoms shouldn't exist. That's a pretty stark contrast to what happens because atoms do exist. And finally, there's a slightly more subtle issue involving atoms, and that is they should radiate a continuous range of wavelengths or colors in visible light as the electrons spiral into the nucleus. We should see a whole rainbow of colors coming from an atom. That's not what we see. What we see instead is that atoms radiate discrete wavelengths. We call these spectral lines when we observe them. And there are different patterns, and the different patterns of these spectral lines are characteristic of each element. So this picture is the spectrum of hydrogen. And the colors correspond to the colors in the rainbow above, but instead of seeing the whole rainbow of color, what we see are discrete spectral lines, one in the red, one in the green, one in the blue, and one sort of deep in the violet. There is a crack in classical physics. Something that should happen, continuous emission of light, doesn't happen. Instead, we get these discrete spectral lines. So we've got a number of problems here in classical physics. So let's summarize. By the late 1800s, we were in a mindset where classical physics, including this mechanical view of electromagnetism, seemed poised to explain the entire universe. We had Newtonian mechanics, we had Maxwellian electromagnetism, and this whole mechanical view, the triumph of explaining the solar system, explaining the energy of particles in a gas that makes up its temperature. All that led to this view that mechanical view of everything prevailed, and electromagnetism would also be explained by mechanical understandings of the electric and magnetic fields ultimately. And then there are these cracks. I say here they're seemingly minor. Some are minor because they're not things you would notice immediately. Some are minor because they're really small effects. But these cracks that we've just gone over are going to open the revolution of 20th century physics. And these cracks are the ether quandaries, which will help lead to relativity, the precession of Mercury, that will help us confirm another theory of relativity, Einstein's general theory, and then the problem of glowing objects, and the fact that they should be emitting infinite energy, but obviously aren't. The problem of electrons and light, the relatively subtle measurements made with that delicate experiment, the photoelectric effect experiment. And finally, the very existence of atoms, which shouldn't exist because their orbiting electrons should, as Maxwell's equations say, radiate electromagnetic radiation. That should cause the atoms to lose their energy, and the electron should spiral into the nucleus, and there should be no atoms, and no physicists to think about it, and no you to view this lecture, and nothing much interesting should be happening, and yet that's not the universe we live in.